Good morning, students. Actually, already I have started this compression unit. Yesterday, I have given some introduction regarding this compression. So, already we have discussed it. The meaning of compression is we want to reduce redundant data in the given image. That is the main aim of this image compression. That means redundant data means the information which is not required as far as the human eye is concerned. For that reason, we will remove certain amount of information from the given image. Okay, so that is called the irrelevant information. Okay, so this can be used in many image processing applications. So actually, why you need this image compression is just we have taken one examples. For example, if we want to record a 2-hour standard definition TV video, we need nearly 24 MB, 224 GB is needed to store that information. So this is very large. It is very difficult, or it can occupy more memory space. So if you are able to remove the redundant data, or if you are able to eliminate the redundant data, then you can reduce the size of the image. Then you can store the given image in a less space. So that is called as a compression, because here in this case we have got a 224 GB, because if you want to store 2-hour standard definition TV video, if you want to store, it requires this much of the zip. So there are so many, actually, for example, if you want to use any DVD to store this information, nearly we require a number of DVDs are required to store it. If you apply compression, then you can store this information on a single DVD. If you are able to eliminate the redundant data. So that is the beauty of this compression. So by using compression, we can reduce the memory size, and also you can transmit the data in a less time. Okay, so what is the objective of this image compression? The main objective of this Image compression is to minimize the number of bits required to represent an image. That is actually I want to represent pixel gray level information in the form of bits. So you can use number of bits to represent the information in digital form. In case of if you want to use 8-bit to code the gray levels, you will have a gray level variation from 0 to 255. That means 0 is corresponding to the black and 255 is corresponding to the white. So in this case, actually, our aim or the aim of the image compression is we want to reduce the number of bits required to represent any image. For example, if you are able to reduce the number of bits required to represent any pixel, automatically the number of bits required to represent an image also you can reduce it. So then the memory required or transmission time required for transmission of the data is reduced. That is the main objective of this image compression. Next one is where you can use this image compression. So there are numerous applications for this image compression. Some of the examples are, one is broadcast TV via satellite, next military communications via aircraft, teleconferencing and computer communication, etc. And the medical in the medical field also we are using this compression to store the information. So now the storage actually we want to preserve the information for future use. So there are some documents which are meant for accuracy. For example, legal document and medical documents are required to store without any loss. That means we should not compress much, or it is not you are not allowed to remove the data from the image. In those cases, the compression ratio is less. But in some cases, in satellite images or in other maps, you can sacrifice some information. Then you can get the high compression ratios. So depending on the application, we can use variable compression methods to reduce the redundant data. In some cases, or in some methods, the removal redundant data is less because we need accuracy in the reconstruction after decompression. In those cases, the compression ratio is small. In some cases, you can allow to more compression ratios. So while decompressing the image or reconstructing the image, there is some loss of information. But as far as I is concerned, it is not much affected. So that's why in some cases we will use high compression ratios. Then you can reduce the memory size or the transmission time. So actually, image data compression methods can be divided into the two categories. The first one is information preserving compression, because the name itself is indicating that in this case we will preserve the information by compressing the image. So especially for the image archiving, that means if you want to store in the form of archives. So in that case, for example, storage of legal or medical records, if you want to store in the form of in a systematic order of legal and mechanical records, we can use this information preserving compression. In this case, the compression ratio is very small. In some cases, it is not compressed. In some cases, you can compress the image with a small compression ratios, or you can remove only a small amount of the data from the image only. Okay, compress and decompress images without losing information. So information preserving system can be used without loss of information. In this information preserving compression can be applied without the loss of any information. That means in this case you will get the less amount of the compression ratios. The second one is the lossy image compression. So in this case, we'll have a higher level of data reduction. That means we will get a higher compression ratios because the original image and compressed image. If you take the ratio of these two, you will get the compression ratio. So in this case, we will have a high compression or high data reduction is possible in lossy image compression. So results in less than perfect reduction of the original image. For example, after decompression of this image, the decompressed image may not be equal to the original image. The accuracy of the decompressed image is very, very less when compared to the original image because we have removed higher level of data from the image, original image. So while decompressing the image, the data which is lost while compressing the image is not added to this decompressed image. So that's why there is a difference in the decompressed image and original image. Both are not equal. So, but in some applications, some tolerance is allowed. That means compression ratios, higher compression ratios are allowed. In those cases, we will use this lossy image compression. So the applications of this lossy image compressions is one is broadcast television and another one is video conferencing. So with this discussion, we came to know that there is a trade-off between image quality and image compression ratio. For example, if you need a high image quality, so automatically the compression ratio is very small. If you are ready to sacrifice the image quality, so you will get the higher compression ratios. So in between this image quality and compression ratio, there is a trade-off between them. If quality is required, we have to lose that compression ratio. If you want a high compression ratio, we have to sacrifice the quality of the image. So in between, depending on the application, we have to select the required parameter, that is the quality or ratio. We have to decide. Okay. So this is the pictorial representation of image compression. For example, the first one. So first one is the original image. The first one is the original image. By applying some method, we have compressed that image. So we'll have a compressed image. This is the compressed image, or this is the compact information. Compact information means we have removed the redundant data. That's why it is called as a compact information. So this can be used for storage or transmission. After compression, you can store or transmission. So this is the compressed image. If you want to display on any monitor, then we have to decompress this compressed image. Then only you can get the image. That is, the image may be equal to the original image, or the image may be a lossy image, depending on the compression which is applied on the input image. For example, here this is I have not specified what type of compression is applied on this image. Just we have mentioned only compression is applied. That means there are some method, compression method is applied on this original image. We got the compressed image. So here, depending on the compression method, you may have lossless decompression or lossy decompression. If you apply lossless compression techniques to compress this image, after decompressing, you can get the low loss image. Low loss image means after decompression, the image may be almost equal to the original image because we are not allowed any loss of information while compressing. That's why the decompressed image is almost equal to the original image. If you apply lossy compression technique to compress the original image, after decompression, there is a loss of data. That's why decompressed image is not equal to the original image. There is a lot of information, or more information is we have removed from the compression operation. That's why the reconstructed image are having less quality when compared to the original image. Okay, so actually this is the process we will apply compression and decompression on the image. Compression is used to store or transmission, and decompression is used to display the image, either loss image or lossless image. So this is the process of image compression and decompression. Okay, so here there are two words we are going to use it. Data, one word, and another one is information. But data and information both are not same. Data is different, information is different. Actually, data is used to convey the information. Data is used to convey the information only. But the data is not the same as the information. There is a difference. Data are the means to convey the information. So here, various amounts of data may be used to represent the same amount of information. So here, various amounts of data may be used to represent the same amount of information. So that means here, for example, if you observe these examples here, so I want to represent this information by using some data. Okay, so the same information here, the same information is conveyed by using low data. So here the same information is conveyed by using the less data in comparison with the previous two. So that means here the same amount of information can be represented by various amounts of data. That means here this I want to convey this information only. Ellen will meet you at log on at 6 p.m. tomorrow night. That's all. I want to convey this information. But this information you can convey in example 1 or in example 2 also. So in example 1 and example 2, we need more data to convey the information. But in comparison with 1 and 2, the third example requires less amount of the data to represent the same information. So that's what here we have represented here. Various amounts of data may be used to represent the same amount of information. Okay, part of data may be provide no relevant information, because if you compare it in this case, in this example, in the first example, some of the information is not relevant, that can be called as a irrelevant data or redundant data. Irrelevant data or redundant data, call it as that data is not required to convey the information. So that data is called as a redundant data or data redundancy. The amount of data can be larger, much larger, expressed than the amount of information. So generally, the amount of data can be much larger. That means the data which is used to express or to convey the information is very large. Okay, then the image consists of redundant data or redundancy in the image. Okay, so that is the difference between data and data and information. Okay, so here I want to explain what is the data and what is the redundant data and what is the information. Here, if you see this diagram, the yellow part is corresponding to the redundant data. Actually, to convey the information, that the redundant data is not required, but only the data corresponding to the information is required. So now the data is equal to information plus redundant data. Both can be considered as a data. So various informations are the same information conveyed in by using different amount of data, because the redundancy may change. So if the redundancy is increased, automatically the size of the image is also increases. It requires a very large amount of memory is required. If you want to transmit, hello, yes, do you have any doubt? Okay, so if the data size is very large, it need very large amount of the memory space. If you want to transmit a large amount of the data, it takes more time. Okay, so this is the difference between information and data. Okay. So which one is called data redundancy or redundant data? Data that provides no relevant information. Because if any data which is not relevant to the information, that is called as a redundant data. Redundant data or redundancy, we call it as a. Image compression techniques can be designed by reducing or eliminating the data redundancy. Generally, we want to design image compression techniques. In those techniques, we can reduce the redundancy to some extent, or you can eliminate completely. You can eliminate the redundancy. So, depending on our requirement or the accuracy levels of the decompressed image, we can use different sets of methods to compress the image. Okay. So in this case, image coding or compression has a goal to reduce the amount of data by reducing the amount of redundancy. So actually, to compress the image, we will code the information in terms of symbols. In terms of symbols, we can code the information in terms of symbols. Those symbols can be stored. But if you want to decompress the image, then the same symbols information is recovered and then it can be plotted as a decompressed image. Okay. So here, image coding or compression, has one goal. What is that goal? The goal is reduce the amount of data. Okay, how you reduce the amount of data? If you are able to remove the redundant data, then you can reduce the data. Okay, by reducing the data, you can get the compression. Okay, so in this way, you can get the reduce the data required to convey the information. Okay, so here I want to define one ratio, that is compression ratio. For example, data set 1, that is one image, that is the original image. Okay, original image, or you can call it as a input image for compressed method or compressing process. Okay, this data set 1 or the image, the input image consists of n1 carrying units. That means bits. N1 bits is having in this. Okay, so after compression, we will have a data set 2. But data set 1 and data set 2 are not equal. Both are different because data set 1 consists of more number of bits or more data. Because after compressing this data set 1, you will have a this compressed image. So automatically some data we have removed from this image, then only we got this data set 2 or the compressed image we got it. So the number of bits in the data set 2 is in less number when compared to the N1. So N1 data set 1 or image 1 image is carrying N1 carrying units. So here this compressed image carrying N2 units. So I want to know the compression ratio. So here this original image carrying how many bits? N1 bits. This compressed image is carrying how many bits? N2 bits. So the ratio of this one will use the compression ratio. Okay, compression ratio. So in this way you can define it. Just it is the ratio of the compressed image to the original image, compressed image data to sorry, original image data to compressed image data will gives the compression ratio. Okay, compression ratio. So here we want to use some basic terms to represent different things in image compression. So the first one is let N1 and N2 refers to the amounts of data in two data sets that carry the same information. Because in the previous case, here we have assumed this is the data set 1, it is carrying N1 units, and this is the data set 2, it is carrying N2 bits, N2 bits. Okay, so here now I want to define the compression ratio. So already we have defined the compression ratio is defined as the number of data bits in original image to the number of data bits in the compressed image will gives the compression ratio. Compression ratio. Okay, if the data bits in N2 is very small, then we'll have a high compression ratios. If the data in original image and in compressed image both are same, then we'll get 1. There is no compression, because input image is equal to output image, sorry, decompressed image. In that case, there is no compression, or redundant data is not there in that image. Okay, so in this way you can define that compression ratio. The next one is relative data redundancy. Relative means we are comparing the redundancy with one. Because here we are considering two data sets. I want to define the relative data redundancy with respect to some other data set. For example, if you want to define relative data redundancy with respect to the data set 1 or N1, data set N1, I want to define it. That is equal to RD is equal to 1 minus 1 by CR will use the relative data redundancy with respect to the data set N1. Data set N1. If you substitute CR is equal to N1 by N2, then RD is equal to 1 minus N2 by N1. N2 by N1. So from this expression, I want to know what is the compression ratio and what is the relative data redundancy depending on the relation between N1 and N2. N1 and N2. So for example, if N1 is equal to N2, that means so there is no variation in the data in original image or in decompressed image. Both are having same information. Then CR is equal to 1 only, because if you substitute N1 is equal to N2, we will get CR is equal to 1 only. And if you want to calculate relative data redundancy, RD is equal to 1 minus N2 by N1. If both are equal, you will get 1. 1 minus 1 is equal to 0. That means the data redundancy relative to the second data set, the first set contains no redundant data. There is no redundant data. Here we are considering with respect to the relative to the second data set, the first set contains no redundant data because both are having same information. That means there is no question of any redundant data with respect to second. Relative to the second data set, the first data set contains no redundant data. If N1 is equal to N2. Similarly, if N1 is much greater than N2, that means it indicates that N1 is very large and N2 is very small, very small. Let us assume it N2 is equal to, for example, 0.001, for example, or 0, we can consider it. Then CR is equal to N1 by 0 will use the infinity. That means if N2 tends to 0, CR tends to infinity. CR tends to infinity. The compression ratio tends to infinity. Then RD tends to 1. Okay. In this case, the relative to the second data set, the first set contains a highly redundant data. Highly redundant data. That means here the compression ratio is very large. Means the image consists of large amount of redundant data. Okay, redundant data. So that's why. Okay. Uh, okay. So in the third case, if n1 is much less, are you getting my voice? Hello? Hello? Okay, then if n1 is much less than n2, in this case n1 is much less. If you assume n1 is equal to 0, then compression ratio is equal to 0 and RD is equal to minus infinity. That is relative to the second data set. The first data set is highly compressed. Okay, so depending on the relation between N1 and N2, we are having different amounts of compression ratios and relative data redundancies. For example, if CR is equal to 10 means, for example, we got compression ratio is equal to 10. So then N1 is equal to 10 into N2. That means the 90% of the data in the first data set is redundant. The first data set is redundant. 90% of the redundancy is present in the first data set. Like that, if CR is equal to 0, then there is no question of any redundant data in the first data set. Okay. So these are the two terms we can use to analyze the compression. Okay. So now there are three basic data redundancies. The first one is coding redundancy. The second one is interpixel redundancy. Third one is psychovisual redundancy. So actually the coding redundancy, CR, it is represented in a short form CR. Some gray labels are more common than others. For example, here in this case, in coding redundancy, some gray labels may occur in a very few, in a rare case. Some gray labels appears in a rare case, but some gray labels appears frequently. So depending on the occurrence or the probability of the pixels, we will assign some code. So probable occurring gray labels are assigned with the shorter codes, and rarely occurring gray labels are assigned with large codes. That means higher probability gray labels are assigned with shorter codes, and lesser probability gray labels are assigned with longer codes in coding to remove the coding redundancy. We will discuss in detail while discussing coding redundancy. Next one is intrapixel redundancy. So here the same gray labels covers large areas. For example, if the same gray label is covering large areas, then if there is any small variation in the gray labels in this large area, because they are very near to that large area average gray level, that is also considered equal to the average gray level only. Okay, that is called interpixel redundancy. Next one is a psycho-visual redundancy. In this case, actually the eye can only resolve 32 gray levels locally. That means if you use 8-bit, we are having gray level from 0 to 255. But I can perceive only 32 gray levels only. The remaining gray levels can be neglected by the eye. So it can receive only 32 gray levels only. So the remaining gray levels we can considered as a redundant gray levels in the given image. So there are three basic data redundancies. That is, the first one is coding redundancy. The second one is interpixel redundancy. The third one is psycho-visual redundancy. So we will discuss one by one. Okay. So here, further, now I want to discuss about coding redundancy. So actually, to code any gray level in general, we will apply m bits. So actually, if you want to code the gray levels in a given image by using 8-bit. So all pixels are coded with 8 bits only, irrespective of the probability or the occurrence of that gray level. Okay, gray level. Irrespective of the probability, we will assign 8 bits or m bit. In general, you may consider 3-bit or 8-bit or some other bits. So a natural m-bit coding method assigns m-bits to each gray level without considering the probability that gray level occurs. So if you are without considering, if you apply, if without considering the probability of the occurrence of the gray level, if you apply m-bit natural m-bit coding, then there is a coding redundancy. Actually, high probability gray levels, if you are able to apply a shorter length bit code, if you apply, if you apply larger length bit code for less probable gray levels, then we are able to remove the coding redundancy. If you apply same m bit to all the gray levels, irrespective of the probability, then there is a coding redundancy. So here, the probability of occurrence of each gray level to determine the length of coding represents that the particular gray level. That is the variable length coding I want to apply it. So depending on the probability of occurrence, I want to apply variable length coding. So frequently occurring gray levels are assigned with the shorter code. Okay. Low probability or rarely occurred gray levels are assigned with larger length coding. So in that way, if we assign coding variable length coding, then we can eliminate the coding redundancy. Okay. Here, assign shorter code words to the gray levels that occur most frequently, or vice versa. Okay. So here, for example, if you consider it, RK is used to represent the random variable corresponding to the gray level. Okay, gray level. So the gray level, that is normalized gray level, occupies the levels in between 0 and 1. 0 and 1, here the let RK is in between these two limits, gray levels. The discrete random variable. This RK is called as a discrete random variable, which is used to represent the gray level. The gray level value is in between 0 and 1 only. So PRE is used to indicate the probability. So here RK, PR of RK is used to represent a particular gray level. So this What is the probability of this RK? Gray level is represented by pair of RK, probability occurrence of RK. And NK is the number of pixels that RK appears in the image.